So three-phase 75 MVA single-phase transformers rated at 39.8 kilovolts, 133 kilovolts are electrically connected in a three-phase bank. Each transformer has a series impedance of 0.97 plus J11.3 ohms referred to its 133 kilovolts winding. So if the transformer are connected to Y, calculate the voltage and power rating of the three-phase connection. The equivalent impedance as referred to its low voltage terminals, the equivalent impedance as referred to its high voltage terminals, and and B repeat A if the transformer is connected to its low voltage side and delta on its high voltage side. So we have a given here which is three-phase connected to 75 millivolts ampere rated at 39.8 kilovolts, 133 kilovolts. So our impedance, which is each transformer has an impedance of G is of 0.27 plus J 11.3 ohms referred to 133 kilovolts winding. So on the low voltage side, the voltage rating of the three-phase transformer is given in this formula. We have square root of 3 times dV. So in the low voltage side, we have 39.8 kilovolts. So we just multiply by square root of 3. So we get uh, voltage rating of 68,935 volts. So in the high voltage side, the voltage rating is just given by the formula is square root of 3 times B. So in the high voltage side, we have for the V, we have 1,333 kilovolts. So we get a voltage rating of 230,362.76 volts. For the total power rating in the three-phase connection, no, in the three-phase transformer bank. So our power rating is we will multiply the NVA rating of the transformer times 3. So we get 225 million volts ampere. So before we can get the equivalent impedance that is referred to the low voltage terminals, we will find the transformer ratio. So our transformer ratio is we will just multiply uh, the high voltage side all over the low voltage side. So our V1, which is 133 kilovolts, is the voltage referring to the low voltage V2. I rather no, our V2 our V2 is which is 39.8 is the voltage that is referring to the low voltage side, and then this 133 kilovolts is the voltage that is referring to the high voltage winding. So we get a transformer ratio of 3.34. So the equivalent impedance referred to the low voltage terminals, which is our low voltage, is we have 39.8 kilovolts, is given with this formula. Now we have C 0.97 plus J 11.3 times the our transformer ratio, which is 3.34 squared. So we have a value for the equivalent impedance is referred to the low voltage terminals. We have 0.08695 plus J 1.0129 ohms. So for 3, which is the equivalent impedance referred to the high voltage terminals. So we have for high voltage terminals now we have 133 kilovolts. So our GEQ is just equal no to 0.97 plus J 11.3. So therefore our equivalent impedance na that is referred to high voltage side is 0.27 plus G 11.3 kilovolts. Given naman po niya po sa question. So 133. That this impedance is referred to the 133 winding. So for Y delta connection, I two, which is we will find the equivalent impedance no, that is referred to the low voltage terminal. So II2 is just equal to the previous one for the Y connection. So the EQ is equals to 0.97 times plus J 11.3 is was over A squared, which is the transfer relation. So we get a value of 0.8695 plus J 1.79 ohms for the equivalence impedance that's referred to the low voltage terminals. So in uh, equivalence impedance referred to the high voltage terminal, which is our high voltage terminal is 133,000. So for a star delta connection, since yung ano natin, high voltage is star delta. So we will, our working formula here is ito siya. Our GEQ for Y connection is yun yung gagamitin natin to find the equivalent impedance that is referred to the high voltage side. Yung high voltage side natin is delta connection siya. So 3 times the GEQ and the Y connection, which is 0.27 plus G plus 11.3 ohms. So we get a value of an equivalent impedance, which is referred to the high voltage terminal, which is 2.91 plus G 33.99 ohms.